Thank you very much for opportunity to talk my presentation. I'm Hidetaka Morita from National Cerebral and Cardiovascular Center in Japan. So I would like to talk about automated IMpella optimized analog system, which is automatic controller of IMpella 5.5. So IMpella supports hemodynamics and unloads the left ventricle. So IMpella reduces pressure volume area support flow dependently. So especially the degree of LV unloading is important. So in several reports, including our report, total IMpella support exerts higher cardioprotective effect than partial IMpella support and large animal model in acute myocardial infarction. So IMpella 5.5 is powerful and have durability. So it enables a wide range of LV unloading levels from partial to total support. However, subtle alteration of pump speed, LV function, or LV loading conditions can dramatically change the LV pressure. So like this, leading to device suction in the LV and unstable hemodynamics. So as a result, higher degree of IMpella support requires sensitive IMpella pump regulation. We developed the automated IMpella optimized unloading system we called AIMOUS. So AIMOUS auto-sets stable LV unloading with using IMpella 5.5. We know the LV systolic pressure is good marker of LV unloading because it's directly related to the size of PV area. So we use LV-SP as the AIMOUS control target. The system operates as a closed-loop controller, and it employs a PI control system. In brief, the difference between target LV-SP and measured LV-SP is constantly feedback, and IMpella automatically controlled according to the difference. So this study aims to evaluate the AIMOUS performance in a GOAT model of cardiogenic shock. So this is AIMOUS control of LV pressure. So from this, after AIMOUS control starts, IMpella rotation speed increasing according to the difference from the target. When the LV-SP reaches the target levels, the feedback regulator adjusts the rotation speed to maintain the LV pressure. This shows stepwise changes of target LV-SP. First, we set target LV-SP at 20 millimeter mercury. AIMOUS controls the LV-SP to the target. After that, we change the target 30, 40, 50. So AIMOUS adjusts the LV-SP to the target level each other. So we conduct the experiment using 6 gourds weighing about 50 kilograms. Under general anesthesia, IMpella 5.5 is inserted through the carotid artery and placed in the LV. Acute heart failure is induced by microembolization of the left coronary arteries and reduce the LV EUF to about 38%, and we can induce the cardiogenic shock with mean atrial pressure about 50. This is protocol 1. Protocol 1 is a verification of the accuracy of AIMOUS control. We compare the target LV-SP and measured LV-SP in 6 cardiogenic shock GOT. So we simultaneously recorded hemodynamics. we changed the target LSP 20 millimercury to 60 mercury, and we compared the value between target LSP and measured LSP. So as a result example, I showed 3 times control on the same individual. Target LSP orange line and measured LSP red line at 3 minutes after the start of each control was compared. In this case, measured LSP and target LSP is almost equal. So we plot the result. The target LSP and the measured LSP were almost equal even at 3 minutes into the control. We found a strong linear relationship between the target LSP and measured LSP. The slope was almost unity, and the y-intercept was almost 0. And we conduct other experiment 2 and 3. Protocol 3 is a blood volume challenge. So we observed LSP and AIMOUS control during blood volume withdrawal and infusion. So we conduct 4 withdrawal and 4 reinfusion at 5 minutes intervals. We compared LSP changes with and without AIMOUS control. Protocol 3 is innatrovic challenge. We observe them during dobutamine administration. So we conduct 2 doses experiment. Low dose is 0.0 gamma and high dose is 1 gamma. So both experiment in single GOT. This is protocol 2 result. So blue triangle marker is withdrawal and pink marker is infusion. So to the left side in the non-control interval, so blue line is IMpella speed is green line is IMpella speed is constant. So in that case, LSP easily decreased with withdrawal and increased with infusion. On the other hand, to the right side in the AIMOUS control interval, LSP remained nearly constant. So because the green line, IMpella rotation speed changed automatically. This is protocol 3 control. So this shows low dose dobutamine phase. In the non-control interval, LSP easily increased with dobutamine infusion. But in AIMOUS control right side, LSP remained nearly constant. So however, in dobutamine high dose experiment, AIMOUS fails to control LSP under the high dose dobutamine. So because the rotation speed green line reached its upper limit, 33,000 RPM. Finally, we discuss the result of this AIMOUS. AIMOUS can control LSP well. For example, during recovery phase, AIMOUS negative feedback control maintain low LSP despite dynamic LV function changes. Second, AIMOUS makes it easier for medical staff to manage IMpella. So because AIMOUS control the LV condition, and the medical staff can focus on the other systemic management. Third, AIMOUS control LSP well. So as a protocol 2 result, controlling LSP compromising aortic pressure now, thus a new system is needed for atrial pressure and systemic perfusion management. That's all. Thank you very much for listening.